Yeah, so thank you for the opportunity to give an update on our ARIADNE Axion experiment, which is an NMR-based fifth force style experiment. It's a collaboration between us at Northwestern as well as folks at Stanford, Indiana University, Perimeter Institute, PTB in Germany, as well as CAP in Korea. And so I don't need to spend any time motivating Axions at this workshop, but wanted to point out that in addition to searching for Axions as a viable dark matter candidate, and therefore being some background field that one can interact with, it's also viable to look for Axions as force mediators, in particular looking for new fifth forces, in our case looking for spin-dependent fifth forces that maybe only show up at short distances, where the length scales we're thinking about are kind of tens of microns. And so the one potential advantage of this technique is that these Axions are sourced locally, and you don't need to assume anything about the local dark matter density of Earth, for example, to do these searches. So if you look at sort of the landscape of these style of experiments, one can sort of characterize them in terms of the source, whether they're dark matter, solar Axions, or lab-produced Axions, and then also in terms of the coupling. So the ARIADNE experiment is sort of in this bottom corner here, where we're looking for lab-produced Axions and coupling to nucleons, whereas I think the vast majority of the work we're hearing about in the field is focusing on searching for the photons. So if you look at the QCD Axion parameter space, it's nicely parameterized by a single parameter, since the coupling is inversely related to the mass. And this is just a summary plot from a nice paper that was put together as part of the US SNOMAS process recently to chart out ideas for prioritizing directions in high energy physics in the US for the next coming decade or so. And so I think, so our experiment here is, at least for the first round, is targeting at Axion masses that are in the kind of 100 micro EV to milli EV range. In the future, that range can expand a bit, but I think it's interesting to look at the exciting developments here with many experiments coming online, where there's really a prospect, I think, to cover the Axion parameter space all the way over its all the way over its allowed values, where there's some bounds at the high end for astrophysics, for example, supernova bounds, and then there's black hole superradiance bounds at the low mass range. And I think it's really exciting that this parameter space is now potentially going to be filled in the coming decades. So in our experiment, as I mentioned earlier, we're looking for coupling to looking for Axions coupling nucleons and looking for a fifth force. And so in particular, if you look at the Axion can have a coupling to a scalar coupling to nuclei, which is proportional to theta QCD, and also a pseudoscalar coupling, which looks like a derivative coupling to fermions. In the non-relativist limit, it looks like the gradient of the Axion field basically dotted into the spin sigma of the nucleons. And so there's a variety of different vertices you can have. And you have two nuclei coming together. You can have a scalar coupling, or a monopole. You can have a monopole-dipole coupling, or a dipole-dipole coupling. And so in ARIADNE, we're looking for the middle example here, where we have a dipole-dipole type of interaction. And the mass range, again, where we're probing is 100 micro EV range up to, say, a few milli EV, at least in the first version of our experiment. So the physics basically looks like a spin-dependent force, as I mentioned earlier. So if you have a fermion separated from some other fermion at some distance r, there's a coupling between the mass and the spin. And so there's some scalar and dipole coupling constants here out in front. And then you basically have a 1/r squared type form, as well as an exponential suppression. So this is basically set by the finite range or the Compton wavelength of the Axion. And then finally, there's a sigma.r piece, which basically allows this interaction to be written down as an effective magnetic field, where now the magnetic moment of the spin couples into this effective field determined by this potential. The range here is set, again, by the Compton wavelength, which from astrophysical bounds, we expect to be less than a few milli EV. So that means the length scales we're looking for here are kind of the 30 scales and higher. And so this magnetic light interaction couples directly to this and therefore is not a real magnetic field. It doesn't obey Maxwell's equations, and in particular for experimentalists, it's relevant that it's not affected by superconducting magnetic shielding, which will be part of the crucial design strategy of our setup. So if you look at the concept for the experiment, this is sort of the core elements of the ARIADNE experiment. We have an unpolarized source mass, which is basically a tungsten wheel with some teeth cut into the exterior, sort of like a gear. And then we bring this wheel in close proximity to the spin sample. In our case, we're using laser-polarized helium as a detector. And then this helium is enclosed in a quartz container, which is then coated with a superconducting thin film to act as a magnetic field to block out regular magnetic interactions between these two objects. And so then we essentially activate the gear here by spinning it, and as the teeth of the gear pass by the sample, then we essentially modulate this effective magnetic field at the frequency that the teeth pass by. And so we can choose to do this on resonance to get an enhancement of the signal, where basically we choose to modulate the field at the nuclear Larmor precession frequency, which is set by some applied field that we use to set the splitting of the spin up and down states of the spin 1/2 helium-3 nucleus. And so then we use a squid magnetometer loop to measure that perturbed magnetization of the sample. And so in this case, the fundamental limit here is set by the transverse spin projection noise, which scales like 1/√² of the volume and the density and the T2, or the transverse decoherence time in this sample. And so for our setup, we can project the sensitivity here. Now this is a plot showing the product of the two coupling constants, the scalar and the dipole coupling on the vertical scale. On the horizontal scale, at the bottom, we have the force range, going down from 30 microns up to a few centimeters. And then the corresponding mass of the axion on the top axis here, going from a milli-eV scale on the left side down to micro-eV scale towards the right. So if you look at the current limits set by precision magnetometry experiments, they're shown in the upper right corner as a blue shaded region. If you combine these limits with astrophysics, then one can carve out this tan, a more aggressive region. But if you ask where the QCD axion is likely to live on this parameter space, it's quite a bit further down in this shaded gray band, where the limits of the band here are set by what we have for the bounds on the theta QCD parameter from neutron EDM. So we know theta QCD is less than about 10 to the minus 10, setting the upper boundary of that band. And then we know there's also a lower boundary to this band because there's some amount of CP violation that we know to be present in the standard model. And so one naturally expects theta QCD to be of order 10 to the minus 16. So this is sort of the range over which one might expect to see the axion. And in our first initial experiment, we're aiming, depending on the T2 time we're able to achieve in the sample, to start to now be able to carve into that parameter space for the QCD axion. In the future, if things work reasonably well, then we envision scaling up the experiment into this sort of projected reach range, where we could potentially carve out a large fraction of that allowed parameter space. And then longer term, if one could imagine using techniques to evade the limits from the spin projection, for example, using squeezing or some other sort of quantum methods, then if you can get down all the way to the sensitivity of the squid magnetometers, it may be possible to think about carving out most of the entire part of that parameter. So in terms of the actual experimental setup, this is what it more looks like. So this cartoon basically is sitting at the bottom of a wet helium-4 cryostat. We actually have 3 sample chambers that are arranged around this tungsten source mass gear. So the gear has 11 segments in it, and the target is that we have we spin this device at a few hertz to have the frequency of the teeth passing by correspond to about 100 hertz for the nuclear spin precession frequency. This is a prototype picture of a tungsten rotor. It's about 3.8 centimeters diameter. The helium cells are a few millimeters by a fraction of a millimeter thick, and sort of a pancake geometry to get close by to the edge of this tungsten wheel with a separation of a couple hundred microns. And our target spin density in cryogenic conditions is 2×10⁻21 per cubic centimeter. So to get this kind of spin density, one needs to use standard techniques to magnetize the sample. In particular, we use laser polarization methods in our lab. We're using something called metastability exchange optical pumping, where you can take helium, excite it to some metastable state, and then optically pump it. And then through collisions, you wind up polarizing the ground state, nuclear spin with a pretty high degree of polarization. So this is some initial tests that we're doing on top of our cryostat, where we're able to get polarizations of nearly 50% now in timescales of only a matter of a few seconds using this technique. And so this will be nice for the duty cycle of the experiment, where we can get near order unity polarizations generated relatively short timescales. So the sample itself is, as I was saying before, embedded in a quartz block that then gets coated with superconducting niobium thin film as a magnetic shield. So that quartz block assembly is now being fabricated with the help from some commercial vendors. But this is sort of a schematic of what that sample with the detector looks like. And so we have the helium in sort of the cartoon here on the left. The helium is enclosed in a spheroidal shaped geometry. We choose that geometry because the magnetic field gradient inside of a magnetized spheroid is essentially zero. It's a constant magnetic field. However, when you place that spheroid next to a superconducting boundary, which is needed for the magnetic shield, then the Meissner effect basically produces an image of that dipole across the boundary, which then spoils the uniformity of the magnetic field. And so one has to compensate for that. So in our case, we use a compensation coils to essentially flatten out the field that's produced from that Meissner image. And then to create our uniform bias field to set the Larmor frequency for the NMR, we can't just simply put a Helmholtz coil around this superconducting enclosure. So we use a half coil, or a D coil, where basically one can use the fact that the image of the current across the boundary here, when combined with the current, adds up to look like a Helmholtz coil. And so this allows us to apply a uniform bias field to set the Larmor frequency. So the sample block is composed of several pieces that are fabricated and then patterned with the relevant superconducting traces for applying current, and then eventually assembled. This is some pictures of some of the in-process assembly work, where we have the helium-3 filling channels, as well as the prototypes of the sample cell, which we're hoping to finish up at some point in the next couple of months. So there are many challenges on this experiment, and systematic effects and noise sources we need to worry about. And so we're also actively working on testing the levels of some of these expected noise sources and sort of comparing with our expectations. So a lot of this testing is in process, or some of it's been completed now. I just wanted to highlight a couple of the things that we've been able to identify and measure and explore so far. So in particular, as I mentioned earlier, we need to have a superconducting shield to block out regular magnetic noise, because we're trying to measure this really tiny signal from the effective magnetic field of the axion. And so we have to worry about things like Johnson noise, magnetic fields from the susceptibility of the material, magnetic impurities, as well as the Barnett effect, which is just magnetization rotating an object. And so we've been working with our partners at CAP in Korea to develop methods of high purity sputtered niobium films, and shown that so far it looks like we'll be able to meet the design specs for the shielding factors that we want, using a combination of those thin films along with thin foils. So this looks relatively promising. We've also been testing the magnetic impurity levels with our partners from the PTB in Germany to see whether we have sufficiently low noise from embedded magnetic impurities in our prototype tungsten wheel. And this also looks reasonably consistent with Johnson noise at this point. So we expect to see, we don't expect to be limited in terms of reaching the design sensitivity from another important consideration in the experiment is to keep this close distance between the sample and the tungsten wheel. And so to do this, we monitor that distance in situ by using fiber-coupled laser interferometers, which will be deployed in the cryostat. And our target is that this wheel basically needs to wobble by less than about 50 microns throughout the course of spinning at frequencies of a few hertz. So far we're seeing from a benchtop test within about a factor of 2 of that. But we're working on improving it a little bit more, but at least it looks potentially within reach that we should be able to get pretty close to the design sensitivity, which ultimately limits how close we can bring the sample to the source. So that's kind of the highest Axion mass that we'll be able to in our setup. We're excited that things are coming together. So we're expecting it from the timeline to complete our initial construction on the cryostat, hopefully by the end of the fall. And then next year, we think we should be getting into the early data taking phase and commissioning phase for the system. Just to conclude then, so this is a fifth Ford style NMR based experiment to look for the Axion, that's trying to search in sort of one of the less explored parts of the parameter space here at this sort of 1 milli-EV range. A nice feature of it is that you don't have to scan over the mass or over a cavity or over a field to search. You don't have to assume anything about the local dark matter density. And it's also complementary to searches for neutron EDM or other proton EDM type experiments. And I think it's exciting for the field in general that when you combine this experiment along with many other planned and ongoing existing experiments, there's the prospect for really having a nice comprehensive coverage over issues. And so with that, let me go ahead and just acknowledge my group in particular, highlighting the names of the folks that are mainly involved in this from our group, and thank you for your attention. I hope